these new technologies that we're seeing emerge in the market. We'll take a look at a bunch of different A.E.B.E 2.0 applications. We kind of split those into two different sections where there's both process innovations, where there's actual innovation that's being done to the process, as well as product design innovation, where you now have these new abilities, these new features you can use on your parts. And then we'll quickly wrap up at the end. And like I said, I can take any questions at the end and answer them live, but feel free to be using that Q&A feature to chat in any questions you have. It helps us track them, as well as my coworker on the line can answer them as they come up live via text. All right, let's jump right into it. Starting with metal additive 1.0. This is an analogy that I like to make a lot, but today's powder metal 3D printers, powder bed fusion machines we've seen over the past 20 years, they're very similar to what we saw with computers in the 1970s, with these 1970 punch card computers. They're these large industrial machines. They take up, entire rooms potentially. They have these dedicated, highly trained, highly skilled operators. They're very inaccessible to the everyday person. Generally you have like one of these. In the 1970s, you'd have one computer for your entire company with, dedicated people running those machines, and you'd have to queue up your jobs. And we're seeing the same sort of thing today with powder metal 3D printers. When I'm talking about, powder metal 3D printers, I'm referring to, powder bed fusion like DMLS or, SOS. There's some real challenges involved in powder bed fusion too. The main challenges really revolve around these 3 points where it's generally too expensive and too slow for broad adoption. Generally we're seeing with powder bed fusion, capital expenditures of about $1 million, and that's to produce about 1 metric ton of parts per year. On top of that, the materials that are available for those systems are generally not too familiar to many engineers. There's some of these special formulations that engineers may not have heard of that were designed specifically for the process. There's no 4140 steel, for example, or tool steels like D2 or H13 or P20. When it comes to cost, there's lots of cost involved with the process. It's not just the equipment. It's actually, you have to do quite a bit of facilities and changes to, incorporate these machines. It's quite a labor-intensive process when it comes to post-processing. I'm referring to having to, actually cut off your supports after the process, as well as do grinding and some other, secondary operations to actually get your parts out of the machine. The system costs are quite high. Even once you have your system installed, the part cost is generally quite high, which led to some very limited applications like we'll talk about. And then again, there's very little automation involved in the process, making it quite slow. And even once you're printing, the print speeds are quite slow as well, generally only about 100 cc's per hour, which made it, quite slow for very, low applications. And all in all, these challenges really led to very limited applications. This high part cost, these slow processing times, they were very specific, low volume applications. Generally, they were applications where they were okay with this high part cost. Generally, they needed high tolerances as well, which powder bed fusion is good at achieving. And then you needed these excellent material properties too. And because of these, limitations, you really saw these limited applications specialized, and you saw many of them in aerospace and medical. And really, the reason for that is just because in those industries, the volumes are generally lower, and the part cost is generally more acceptable to be higher. So, this is kind of what we've been seeing for the past 20 years, in terms of with powder bed fusion and metal 3D printing to date. But here at Desktop Metal, we really feel that metal 3D printing has barely scratched the surface. And that really it's time to usher in this new age of metal 3D printing that's really for everyone. Because to date, it's been, too industrial and too expensive for prototyping. Generally, you can't justify printing prototypes just because it's too expensive and it's, the process is too inaccessible. And then when it comes to volume production, with actually producing end use components in volume, it's just not fast enough or cheap enough to allow for that to happen. But like I said, we're talking about today, it's time for this new age of additive, whereas really what we're calling is additive 2.0. Today, we're going to be talking mostly about metals, but this also goes along with some plastics as well, really ushering in these two main points of where additive is now moving to in the 2020s. So, what is additive 2.0? Additive 2.0 really revolves around these two main themes. The first one is accessibility, both in terms of accessibility to the actual products, as well as accessibility of parts. So parts that may have been, too expensive or too difficult to print in the past can now be justified thanks to these new lower cost accessible metal 3D printers. It's, the part costs have shrunk, as well as the ease of use of the equipment is far more accessible to everyday engineers, that it makes it much easier to print components now. And we'll look at a lot of examples of this where we'll look at some parts that you may think are relatively simple geometries, but we're still seeing tons of cost savings and time savings thanks to these low-cost, accessible metal 3D printers. The other side of this is high-volume manufacturing, and generally this revolves around binder jetting. What used to be a relatively niche manufacturing process, used to maybe produce maybe one or just a handful of parts via powder bed fusion, can now be used to actually mass produce metal parts, where we're not talking quantities of 5 or 10 like you do generally in powder bed fusion, but we're talking thousands, tens of thousands, even millions of parts per year, thanks to the speed that's allowed via binder jetting. And we'll review that and we'll talk about how that's possible and look at a bunch of I got tons of parts with me here today that we'll talk about, and we'll look at it in detail about how binder jetting allows these parts to be produced in mass form. So a little bit about Desktop Metal. Desktop Metal was founded in 2015 with the goal to make 3D printing accessible to engineers and manufacturers. So the goal of the company really has always been tied to this idea of additive 2.0. But we really want to usher in this new age of accessibility, where everyday engineers, everyday manufacturers can turn to metal 3D printing to solve problems. So how do our products actually enable this ability of additive 2.0 and enable those themes that we were talking about earlier? Today we have 3 systems on the market. There's the Studio system, which you're seeing on the left, 3 metal printers on the market, I should say. We also have a composite printer, but when it comes to metal, we have these 3 machines you're seeing here. On the left, you see our Studio system. That's really our office-friendly printer. It's great for prototypes, one-off components. It's extremely accessible. So how does this enable AM 2.0? It enables you to print low-cost metal 3D parts, as well as has this unprecedented level of accessibility. You can bring that machine into your office environment. I could have a printer sitting next to my desk here. If I was in the office, I would have a printer next to my desk here. Very, very easy to use. Very, very accessible, making it possible for everyone to metal 3D print components. Then you have the shop system, which is really great for batch production with these fully dense, customer-ready, end-use metal parts. AM 2.0 enablers, you have these isotopic material properties that are very important for end-use components. And again, you still have that same level of accessibility because it's a turnkey solution. We're giving you everything you need to start producing hundreds of metal parts a day. Then on the high end of things, you have the production system. The production system really unlocks the speed needed for mass production. It's designed for the factory floor. It enables you to produce thousands, even tens of thousands of parts a day, really unlocking the potential for mass production. It uses these tried and tested metal powders. We'll talk about this in a minute, used in the metal injection molding industry, but it enables you to have low-cost metal 3D printing for very, very high volume production. Going forward, I'm going to refer to these 2 systems generally as binder jetting. The system on the left is called bound metal deposition. We'll talk a little bit about how that works, but just to understand that these are slightly different processes. So let's do it right now. Let's talk about how these systems actually work. At Desktop Metal, we chose to build our metal printers around the chemistry and supply chain of metal injection molding. I'm not sure how many of you today are familiar with metal injection molding, but metal injection molding is this powdered metal process. It enables you to create these highly complex shapes and then mass produce them utilizing these inexpensive metal powders. You can see the wide variety of different geometries on the right here, many different shapes and sizes. It has widely accepted and validated standards, ASTM and ISO standards, allowing you to produce parts in a broad range of different materials. It's used in almost every industry you can think of, heavy use in automotive, medical device, consumer goods, firearms. It's really used across the board. So like I said, our metal printers are based on this technology. So let me first briefly explain to you how metal injection molding works. Metal injection molding starts by mixing a metal powder, a steel powder, for example, with a polymer binder, which is similar to a glue. This creates your feedstock. You then inject this feedstock into a mold the same way you would with a plastic component to create the shape of your part. This shape is that combination of metal powder and polymer binder, and it's still pretty fragile. It kind of has the consistency of like a crayon. If you were to drop it, you could probably break it. But just so you know, at this point, it's metal powder and binder holding that part together. You then go into a solvent debind. That's going to be like a wash that's going to remove most of that binder material out of your part, and then you put it into a furnace. The furnace is going to get up to about, depending on the material, just below its melting temperature, actually sinter that component into a strong, dense metal part. So one thing we're going to talk about a lot about today is the big issue with this process, which is the molding step. And of course, what comes along with molding is tooling. There's huge investments required for the tooling required for the actual shape creation. And as you can imagine, for each different shape you want to create, each different part you want to create, you're going to need a different mold. And we'll talk a lot about that tooling creation and how binder jetting and additive manufacturing eliminates the need for that tooling. So comparing our processes to metal injection molding, like you just saw, you have these 4 steps here. With the studio system, rather than creating a loose powder feedstock, we create rods. That rod is that combination of metal powder and binder, but now it's in a rod form that's totally safe to handle. I wish I had one with me here today. I'd show it to you in front of the camera, but it's just a rod of that same mixture. Rather than creating that part via molding, we're simply going to print those rods layer by layer. It's the same as an FDM process. It's widely used, highly researched. Everyone, I assume most people on this call know about FDM printing, but you're just extruding our rods through a nozzle, printing the part layer by layer. What comes off the printer is very similar to what would come out of the mold in metal injection molding. It's that combination of metal powder and those binders. You then put this part into a debinder. It's going to remove most of that binder material, and then you put it into the furnace. Furnace is going to get just below the melting temperature of that material, and then we're actually going to remove that last bit of binder and sinter our part into a dense, strong metal part. Here's an example. This is a part printed on the studio system. Just to show you, this is strong, dense steel. Probably was really loud. I apologize. Moving on to our binder jetting machines. We have our shop system and the production system, again, based off this metal injection molding process. Here we do use a metal powder. We're going to then create the shape in the printer. I have a few more slides of exactly how binder jetting works, where we're going to actually spray our binder onto our layer of powder, layer by layer, allows us to print very quickly. And then here we're able to do our debinding step in the furnace, so the parts can go, straight from printing into depowdering into the furnace. So just to go a little bit more in depth about binder jetting, because I want to make sure you totally understand this process, let's first look at conventional binder jetting. The way that conventional binder jetting works is this 4-step process generally. You first have your powder deposition, which is that layer of metal injection molding powder. You're then going to spread this powder and compact it to ensure that you have a nice, even, solid layer of powder. You're then going to deposit your binder on top of that layer of powder in a scanning process. The scanner head is going to move in, kind of like this zigzag that you're seeing on screen here to deposit, just the binder, on the layer of your part all over this bed of powder. You're then going to dry this layer of powder. So this is how conventional binder jetting works. And you can see it's a 4-step process, and each layer is actually is quite long. But what Desktop Metal did is we really accelerated this process. So starting with the shop system, we're able to consolidate, from 4 steps down to 2 steps. So rather than doing, powder deposition and then compaction, we're able to do that at the same time with one roller. We then do binder deposition with a single pass. So we have a print bar that's the entire width of the entire build volume that's going to lay down entire level of binder in just a few seconds. So we can print entire layers in just a few seconds here. And then with our binder systems, generally they don't always need to be dried. Taking this one step further to the production system, which really allows for this very, very, very high speed. In the production system, the entire process is consolidated into one head that's going to move across the entire build volume. So with one pass, we're depositing powder, we're spreading that powder, and we're depositing binder. And then once it clears the build volume, it's able to do the exact same thing in the opposite direction. This allows for very, very, very high printing speeds. So just to show you, from conventional binder jetting, which, you may have seen on the market already, to some of the newer products that Desktop Metal has, like the shop system and the production system, which really accelerate printing. And like I mentioned, this idea of single pass jetting really unlocks the speed needed for mass production. You can take a look here at the carriage. This is from the production system. You can see that, of course, it's symmetric across both sides to allow for all 4 of these steps to happen when it's moving in both directions, to allow entire layers to be printed in just a few seconds. The final step of this process, of course, after you've done your printing, is going to be sintering. Sintering is, it's been used in metal injection molding for a long time. It starts by, just doing a ramp up where you're going to do your thermal debind. That's going to remove that binder material out of your part. This is done either by degradation, which is an interaction with the gases in the furnace, or by evaporation, where you're literally just boiling your binder out of your part. You then get up to a temperature just below the melting temperature of the material to allow for sintering to happen, where you're getting this densification, pore removal. We're getting densities above 99%. You're then going to cool down your part to a temperature where it can be removed from the furnace and it's ready for your end use applications. These metal injection molding powders really enable you to fabricate complex parts with really great metallurgical properties. So this is just an example. You can see this chart here where you can see the L here that is showing the properties for a rock material with different materials, and you can see that NIM kind of falls just below that, but you're still getting excellent material properties that are excellent parts for a variety of different applications. Another really important thing to remember about powdered metal parts and with our printed parts is that this idea of sintering. Sintering parts are composed of dense polymer-free metal. So after the process is complete, you no longer have any of that binder remaining in that part. Another thing to remember is that the history of the part and its powdered metal origins have been completely erased. The grains of the metal have grown much larger than the original powder particles, and this is something important to remember about sintering. And this has long been associated with 3D printing, that your parts are not going to be the same strength in different directions because of the layers. Because of sintering, we're raising the entire part up to just below its melting temperature. The entire part is going to be isotropic. This homogeneous microstructure is what makes these parts so attractive for so many different applications. Because these parts are isotropic, you don't have any memory of the part being printed or that it was ever powdered metal. But if you were to section it in all different directions, the microstructure is going to look the same. This is a huge benefit of sintering and of binder jetting technologies today. Okay, so we talked a little bit about additive 1.0, additive 2.0. We looked at how these technologies work, but now let's jump into the applications. Let's talk about what kind of parts people are printing today, what kind of parts are great for this system, and how they're adding value. Like I mentioned earlier, we kind of split these parts into two different sections. We have process innovation, which is benefits like tooling-free manufacturing, the supply chain re-engineering that's possible with these systems, and things like real-time tooling. And then you have your actual product design innovation, which is things like new features that are possible with this system. And let's jump into it. We're going to start by talking about process innovation, and we'll start by talking about tooling-free manufacturing. Let's start by taking a look at some of the most common traditional manufacturing methods for mass production. I'm sure many of you are familiar with these methods. I'm sure many of you are using them today to produce parts. So let's talk about machining, casting, and powder metallurgy. Powder metallurgy, I'm referring to metal injection molding and press and sinter technologies, kind of like what we were just talking about. So used today to produce millions, if not billions, of parts a year. But what are the challenges with these technologies to date? Long lead times. Generally, you have this tooling step where you need to invest in hard tooling to create your part. That tooling can take 8 to 14 weeks, depending on the process, and adds a great amount of cost and lead time to your components. You have these large non-recurring engineering costs in both the design of the tooling, which is highly skilled labor, as well as the fabrication, which is also highly skilled labor, where you need a tool shop to create these highly precise, difficult to produce molds. Generally, especially with casting and powder metallurgy, they're very industrial processes that are not accessible to everyday engineers and manufacturers. I'm guessing most of you don't have powder metallurgy in your building unless you're from a powder metallurgy company, of course, or a casting house inside your company. And then specifically when it comes to machining, these custom high volume machining, you generally need these custom fixtures and that are going to add significant time and cost to the process and to the part. So the result of this is generally it's taking months to bring up a production line. You're seeing far less design iteration because you have to have your design totally finalized before you start producing any of these components, because you really don't want to make changes to that mold once it's been produced. Generally, you're sacrificing some design optimization for ease of manufacturing. You're kind of bending to the will of the process rather than letting the design line run free, designing the best part possible for the process. Specifically with casting and powder metallurgy, generally you can only justify these very high quantities because you need to, make sure you get maximum lifetime out of your tool and you're amortizing your tooling costs. So let's look at what some of the setup times for these processes look like. So with machining, I've talked to many machine shops that are looking at 3D printing, and I ask them, when you get a PO approved, what is the process until you begin high volume production? Generally they're looking at 4 days of prep time where they're determining tooling and work order solutions. They're determining what cutters are going to be best for the process and programming the cam. They're then going to do some pilot runs where they're doing a lot of iteration, doing some inspection where they're iterating on both the tooling as well as the actual cam programming. Then they're doing some of this actual validation with the customer before they actually begin high volume production. It generally is about 1 to 2 months we're seeing before they actually set the machines free, let them run so that they actually cycle parts in high volumes. What does this look like for casting? We're seeing even longer, from 1 to 2 months, potentially up to 4 months. That's because we now require this molding. Looking at an investment casting process over here on the right, generally you have to do this mold design, some iteration of that mold, and the actual creation, which can take quite a long time. You then have to do all this wax injection and slurry coating, your knockout, your actual casting process, and then all the post-processing that's involved after the casting process. Generally, you're seeing, 14 weeks before you even begin production, and then, quite a few weeks in terms of this wax injection and slurry coating to actually begin this volume production. When it comes to MIM, we're seeing the longest lead times generally. This comes down to the fact that you're using these, these very hard to machine, highly precise tool steels, where you're having, long tool builds, all this engineering setup as well, and fixturing design for post-processing. Generally, we're seeing around 5 months. On top of this, what happens if you want to make a change to the design now? Once you've invested in this hard tooling and once you've invested in this process, it's going to be very, very costly and it's going to have very long lead times associated with it to make changes to the design. On the contrary, what does binder jetting look like? To start beginning mass production with binder jetting, generally we're seeing 1 to 2 weeks, where really in the same day that your part is ready, the design is signed off on, we can begin printing within an hour or two. You can have hundreds of parts the next day. You can confirm that the parts are exactly what you want. Maybe you're doing a quick pilot run. You want to put a couple parts through the process first before you start producing thousands or hundreds of thousands. But we're shrinking these 1 to 2 months down to weeks. We're no longer talking about months. We're even talking about days where, in the first day that a part can come into a binder jetting shop, we can have hundreds printed the next day and ready to go in CT powder. And then another important thing, what happens now if the design changes? Rather than having to go change this tooling, all I have to do is change my file. I go into my CAD software and make some changes to a hole or maybe to a fillet or a radius. All I have to do is make those changes in a few minutes, send it back to the printer, and I can have hundreds of those parts ready in just a few days, printed in just a few hours. So really seeing this agility and flexibility that's possible with binder jetting is a huge advantage here in binder jetting, both with consolidating lead times for mass production, as well as flexibility for the actual process. So, the solution to these, traditional, some of the challenges we looked at with traditional mass manufacturing methods is binder jetting. And binder jetting without the need for tooling. Let's take a look at a couple of part examples. I have a power steering joint here. I'll try to hold it up to the camera. Hopefully you can see some of the detail on this part. I really like this part because you can see the spline teeth really well. I don't know how well that's coming across in the camera on my webcam here at home, but this is a joint that's used to transfer power from an electric steering motor to the actual steering wheel and your power steering assembly in a car made out of 17-4 stainless steel. On the production system, the P50 machine, this part can be produced for just $2.52. I can do 646 of these parts in one build, which takes 4 hours, and we're seeing a throughput per year of over 1.2 million parts at just $2.50 a part. Important to know, if I want to make any changes to the part, I want to change the spline, I want to change the number of spokes, simply change the CAD model, send it to the printer. The next day I can have 640 of these, in 4 hours, not even the next day, I can have 640 of these parts printed and ready to go into the next step of the process. Another great example, I'm sure you are all familiar with your locks, in a door or in a car. This is, a steel lock for an industrial process. This part was printed on the shop system. You can see, some of the high resolution here of the keyway, and try to show it the best I can with the webcam that I have with me here today. But again, printed in 17.4 stainless steel, just for $4.70 a part. In a shop system build, in a 16-liter build, you can do over 1,000 of these parts per build. You can do about 9,000 of these parts per week. So as I'm sure you're seeing, we're really talking high volumes now. With binder jetting really for the first time unlocking the cost per part, as well as the throughput that's needed to go to high volumes. Looking at this fuel swirler that you're seeing here, this is used to push a fuel mix into a burner for, I believe it's a generator application. Again, this part was printed on the shop system for just $4.95. Can do over 600 of these parts per build and at around 5,700 of these per week. Again, if I want to make any changes to the design, I want to maybe the fuel mix changes and now we want to change the vein geometry, the angles, the number of veins. All I have to do is, make some changes to my CAD file, upload it to the printer, and in a few days, I can have hundreds of these ready to go into their application. All right, so that just about wraps it up for tooling-free manufacturing. Let's move on to talking about supply chain reengineering. Today, there are a small number of these very large factories. You're seeing these, these large multi-tier distribution networks that at any point there's trillions of dollars of goods being shipped all over the world at any moment. Generally, you're seeing, 3 to 6 months of time between where the parts are actually being produced in the factory and the actual end-use customer. And generally, this is due to it just being more efficient to have these very, very, very large factories that have many processes involved all in, one location than it would be to, manufacture on site, manufacture, closer to your end user. But now with printing, we can kind of, usher in this age of the digital warehouse, where we're now able to print what you need, when and where you need it. No longer, do you need to have these centralized production hubs, but now you can strategically place printers around the world to optimize printing on location, because the part cost is not going to change drastically depending on where you're printing it, because you're using the same powders and the same manufacturing process. You can greatly minimize these shipping and warehousing costs because you're able to do things like, just-in-time operations, where you're able to very closely match your production rates to demand, because, if demand changes, you can simply just add a few parts to the build, run an extra build to very closely match that demand to, minimize these warehousing costs. On top of that, you can be very, very flexible. These manufacturing floors can become very agile to react to demand, to design changes. You can swap over to a new design in just a few hours. So, if I want to print this in the morning, and then, when that job print finishes and I want to print this, here in the afternoon, no problem. Just switch it over, and then, I can have hundreds of different parts produced in just one day. We've been talking a lot about high volume applications, but of course on the studio system, there's also great opportunities for some of these low volume applications. For example, this is a drill here from, located down in Johannesburg, South Africa. They unfortunately had their sun gear break, used for, mining applications. They need to replace that part. They were getting that part from a foundry in China with about a 6-month lead time. Rather than having to, wait that 6 months and have this drill be down, they're able to fire up a printer, print a part in just a few weeks. They actually did a little bit of post-machining and some hardening operations as well. Put it into the drill, get it up and running in, in just a few weeks instead of that 6 months that it would have taken from the foundry. So you're seeing lots of these low volume applications for, replacement parts or tooling for the manufacturing floor. Maybe the original part production has since shut down or is cost prohibitive to reactivate. And then you see a lot of these decade-long service agreements. For example, maybe I buy a backhoe or some piece of construction equipment that comes with a lifetime warranty, and I have some weird, strange part of the brake unfortunately needs to be replaced. I go to my OEM, and they haven't made that part in years. Rather than having to find someone to make it or find a casting house to make it, they can simply load the file onto the printer, and in a couple of days they're ready to ship it out to the end-use customer. And then, of course, there's these opportunities for high-volume manufacturing, where you can have these agile factories that can produce a variety of different parts located around the world, really closing the gap from, where the parts are being produced to the actual end user, because no matter where you're producing the part, much of the part cost is going to stay the same, and the process is going to stay the same because you're running in the same inert environment, in the same system. Continuing on that idea of some of the more low volume applications that are possible due to the accessibility, we can talk a little bit about real-time tooling. Of course, we talked a lot about eliminating tooling altogether, but for the near future, at least, and there's going to still be a need for tooling. Many applications, many parts will still benefit from being produced in high volumes with some of these traditional manufacturing methods. But there's a lot of benefits to actually producing these tooling components because they're almost always produced in low volume. They're almost always extremely expensive. So some of the benefits of this real-time tooling, you can bring up a new production line very quickly because rather than having to go out of house or use one of these traditional methods that are very expensive, I can simply just load my tooling up onto the printer. A couple of days, I'm ready to install it in my manufacturing environment. You can lower your capital expenditures on these maintenance, repair, and operation parts, these MRO parts, because again, we don't need to warehouse components. We can do just-in-time operations. We can, very quickly, when a part needs to be replaced, print a replacement in just a couple of days. And then you're going to see a much higher production line uptime as well, because we're not having to shut down our equipment for multiple days. Just to show you a bunch of examples, we have tons of tooling examples that have been printed, but things like mold inserts that have been printed with conformal cooling channels to allow for accelerated cooling and faster injection molding cycle times. Zipper mold inserts for zinc die casting, coining fixtures, extrusion dies, sheet metal tooling. Lots of different applications. I'll talk through a couple of them in a bit more detail. But really great opportunity. These are just some more examples from some of our customers. E.E.B.E and Egger Tool and Die. I can show you this This is an electrode holder. It also features a channel that snakes through this part because as it's doing this, as the electrode is doing its induction heat treating, it gets very hot. So it's beneficial to cool this part. You can see some of these end effectors as well for holding different parts in the manufacturing environment. You can see kind of that texture and grip that's printed right onto that part. But very beneficial to be able to actually lightweight this part as well, throw it onto the printer, and in a couple of days, I got this part up and running in my manufacturing environment. So, great opportunities for real-time tooling. Here's an example from one of our customers, E.E.B.E. They had this, old robotic gripper that was, operating. They needed to bring up another production line. Rather than having to go find more of these old grippers or have more of them produced, it was much easier for them to simply, put a couple of these parts on the bed, print them, and in a few days, they have their new grippers on the robot ready to operate in their manufacturing environment. Another example, this is a great example of actually optimization using 3D printing. This is a timing belt pulley. It's driven by a servo motor. The original design was based on this aluminum extrusion. It had these collar plates that were clamped on either end. It also required some extensive machining to get it to work. And they really wanted to optimize this part, make it less expensive to manufacture because they needed more of them. They wanted to lighten the weight, and they also wanted to lower the inertia to allow this part to actually run faster. And you can see that optimized design on the screen there. You're going to see that they were able to consolidate the entire assembly into just one component. Of course, this is where you would mount this part onto the servo motor. So what used to be a multi-part assembly featuring screws and clamp collars and things like that can now be just consolidated down into one part by itself. So just a great example of another manufacturing environment component printed on the studio system for one of our customers, E.E.B.E. Another part from one of our customers. This is from Prezioso Francesco. Apologize if I messed up that name, but it's part of a paneling machine. This component is coupled with a gear. It allows this arm to rotate for a sheet metal application. Generally, it was taking them about 7 days to receive this part, if in stock, even longer if it required machining, and it was costing them about 60 euros to produce. They were also having some issues with the original components with them failing. You can see some tear out that occurred here on the part. So they quickly grabbed one of these, modeled it up, and were able to print some of the replacements here on the studio system, making the part stronger because they're free to modify the design to add some increased strength. Faster, they were able to manufacture 6 different samples in just 4 days, and cheaper at just 15 euros per part versus 60, and then much less waste too, of course, because we're printing additively rather than doing it subtractively. One note about this part. In the past, with powder bed fusion and traditional metal 3D printers, laser-based systems, you would never see someone printing a part that looks like this. It would have been far too expensive and the geometry far too simple to justify printing. But now with these lower cost systems like the studio system, it's much easier for this company to simply throw a few of these onto the studio system and they have their part in a few days rather than having to go to their machinist or go to an outside manufacturer. So this is really hitting on that idea of accessibility we're talking about, where we're really lowering the bar of what it takes to justify printing parts, where now they can simply just print these parts, and they have the cost per part needed to justify doing this. So just want to reiterate that with these new technologies, the parts don't have to look as crazy complicated as they did in the past, because we can justify them with these lower costs and easier use of printing. One more quick manufacturing part before we move on. Just another test stand oil-filled nozzle here for our customer Eden. You can see this is actually kind of quite a complex geometry that features a nice internal channel, but able to very quickly print this component for them and get that installed in their manufacturing environment, get them up and running, really reducing the time it takes for them to tool up. Okay, so that was our process innovation section. Let's go ahead and move on to the product design section. A lot of this section is going to revolve around this idea of complex geometry. One note about complex geometry, which is something that I have been talking about a lot, is this idea of justifiable. People have been able to print or produce complex geometries via CNC machining or casting for a long time. But generally, you were kind of designing for your manufacturing process, and if you didn't need a feature, you wouldn't include it because it would add cost to your part. But now with printing, since it's an additive method, we can include a lot more of these features that are actually beneficial for the application, but we couldn't justify because they added cost before. And some of these features actually reduce cost with 3D printing. And we'll look at that, especially when we're talking about lightweight. So just some of the different features we're going to talk about today, with generative design, things like non-circular holes, lightweighting like we just talked about. We'll look at some fun gyroids and features that are possible with 3D printing, internal channels, assembly consolidation, and some undercuts. So starting with generative design, this is an example. This is a bracket that's used on a motorcycle. And you can see that kind of complex webbing features that are involved in this part to allow for a great increase in lightweighting, where we're really optimizing this part for for the application rather than the manufacturing method. Another important thing to note here, we're now not just producing one of these for some special motorcycle we're making, maybe some racing motorcycle, but now I can produce hundreds of these parts, thousands of these parts per day potentially. So that way I can actually go to end-use parts with these kind of designs. These designs used to be, very, very exclusive to these low volume, very specialized applications. But now I can, in the next 20 years, next 10 years, you're going to start to see parts that look like this everywhere, because the cost to produce these, ease of producing these parts is greatly being lowered. Another great example here, this is a BMW race car. They wanted to replace the engine with a different engine. They need to replace some of the brackets to actually hold that engine in place. So what did? They were able to actually scan the original bracket and the mounting locations. They were able to load it into a generative design software, allow that part to take its shape, but optimizing itself for both weight as well as making sure it's still located in its mounting locations. And then we're able to actually just print that part in a few days to actually have this perfect optimized bracket for this application. So you can see this part's actually very organic, has some great curvatures to it, and it's very low cost to print compared to producing a part that looks like this with traditional manufacturing methods. You can see this part was actually bigger than the build volume of the studio system. So you can see it's actually 2 printed parts that has been welded together. Just so you know, if any of you were seeing that, that's actually a weld line between 2 different components. But you can see, it's actually, here it is in that V8 engine. As you can imagine, this engine is very heavy. So these steel components held up very well. And this car is, racing around today. A good example of, a low volume application where we can now, print some of these highly optimized components. Talking a little bit about non-circular holes and some of the benefits of non-circular holes. The part we're going to look at here is a part from one of our customers, John Zink Hamworthy, a combustion company. They were tasked with increasing the performance of this atomizer on this liquid natural gas tanker. When they were tasked with the challenge, the atomizer was only getting a burner turn down of 15:1 during low load. What does that actually mean? It means that when this ship was going slowly, it got very poor fuel efficiency. So they were tasked with, how do we increase the fuel efficiency of this machine, of this boat, I mean. So of course, they very quickly turned to additive manufacturing and look at a lot of different designs, a lot of different geometries on how they could optimize the mixing of the fuel and steam. They very quickly realized that, by using these different oddly shaped holes, it was going to actually increase the performance of the part, increase the mixing to allow for a better low load burner performance. You can see a couple more iterations here and kind of this journey to the final design. And then you can see the final design here with these kind of oddly shaped holes that would have been very difficult if not impossible. This part is actually impossible to machine because it also features some heel-looking channels throughout the part, but they were able to radically redesign the part to be much more fuel efficient. So, they were able to enhance this burner turn down from 15 to 1 to 25 to 1, about a 67% improvement, which resulted in a customer fuel savings of about $90,000 to $160,000 annually. They were able to produce this part in the studio system for just about $300, taking about 5 days. So, as you can imagine, a huge win for John Zink and a huge win for metal 3D printing. This is a cool part. You can see it actually firing here in the atomizer, atomizing this fuel and steam mixture to propel the ship forward. Let's talk a little bit about lightweighting now. You can see, again, we're able to use some of these generative designs, some of these organic shapes to greatly lightweight parts while still making sure we achieve the stiffness and the strength needed for the component. You can see the original design of this pedal here weighing about 1,300 grams and the new design weighing just 586 grams. Important to note that with any other manufacturing method besides additive manufacturing, that new additive, that new design with those organic shapes, those cutouts, would be far more expensive to produce than the one that you're seeing on the left, because it's much more complex to create. It features many cutouts. If it was to be molded, it would feature lots of tool complexity. But with additive manufacturing, now we've gotten rid of 700, 800 grams of material. That's going to result in savings on the part, because since we're printing in a powder bed, we're printing this part layer by layer. That reduction in material actually leads to a reduction in part cost, which is something that is really unheard of in manufacturing, where we're actually able to increase the complexity of our part while lowering the cost. And again, now thanks to binder jetting, we can actually mass produce parts that look like this. Able to produce 30, 40 of these parts in just a few hours, where to date you will maybe see one of these for some very, very special application. Another example here, this is just a fun sensor holder that was benefited from being lightweighted. You can see that kind of gyroid infill throughout the part, but making sure that it's maintaining the rigidness, stiffness needed for the application, but greatly saving weight. And again, adding tons of complexity to the part thanks to these features, but actually reducing the cost of this part because we're removing material out of the part. Another example of this, just a lightweighted bracket. You can see features some of that, very complex webbing and latticing features involved to, again, lightweight this component and remove material from this component. One more before we move on from lightweighting, just another gear. As you guys may have told, I have tons of fun adding lattices to components, so that's why I got quite a few examples here. But just a gear here that features this nice latticing component to remove lots of material out of the component, and then actually still provide plenty of stiffness and strength to the component. And again, it's not just that now I can produce one of these parts, I can print over 100 of these parts in just 4 hours. And some of the big benefits of lightweighting, it's this term called mass decoupling. If you were to look that up, mass decoupling is commonly associated with automotive, but the idea that as you remove mass from a component, it kind of compounds down throughout the car. So in a car scenario, if you're able to lightweight the chassis, you can now lighten the suspension. And if you're able to lighten the suspension, now you need a smaller motor. And it really compounds. So with an example like this, maybe we're able to pull half the weight out of this component. Now we need a less expensive bearing. Now we need a less expensive motor. So there's really these hidden benefits to lightweighting that really compound down throughout your entire assembly that I really encourage you to look into. Moving on to some more cool features, talking about internal channels. Internal channels are really beneficial, especially when it comes to cooling and mixing. You can see this heat exchanger on the left here, printed in copper. I have the bottom half of one here. You can see that channel kind of starting to snake up through the part, comes in here and goes around and sort of snakes up through the component. Excellent for cooling applications. This part's for an oil and gas environment where you're going to have a hot fluid moving through the center of this part, and you're going to have that channel wrapped around with the cooling fluid to pull heat out of that fluid. On the right, you have this injection mold core. Again, in injection molding cycle time, Cooling can be up to 90% of the total cycle time, which, so of course, consolidating that cooling time is very important. And one of the best ways to do that is by incorporating these conformal cooling channels that very closely match the molding surface to allow to pull as much heat as possible out of that mold to consolidate your part, get it out, and get that cycle time as quick as possible. Another benefit, assembly consolidation. Today, so many parts are designed for their manufacturing method, more so than their actual end-use application. So for example, the original model, the original one of these parts, it was printed, or sorry, not printed, it was, the center part here, the actual roller was machined on a lathe. You then had these two gears that were produced via, a different manufacturing process. Then you had this entire thing assembled into one component. The reason that that was being done is because it was cheaper and easier to do it that way than it would be to produce this entire assembly as one part. When it's, it's very beneficial to produce it as one part because you don't need an assembly, you don't need to track 7 different components, you just have one component to worry about. Of course, with 3D printing now, we can consolidate this entire assembly into just one part. So, simply because now with an additive process, we're building up our part layer by layer, we're not increasing our part cost by doing this. We're able to just consolidate all these features because we're only putting material where we need it versus a subtractive process that would have made this very, very difficult to produce. And again, sticking on theme here, it's not just that we're going to produce one of these parts for some special application. Now I can produce hundreds of these, thousands of these parts per week. This is part of a linear actuator, commonly used in a power plant application for opening and closing pilot valves. But this roller screw linear actuator, right now I can actually go to market with a part that's 3D printed because I can produce hundreds of them per week at a cost that makes it cost effective and adds a ton of value to my company by doing this. Last point we'll touch on before we wrap up, I can take a bunch of questions at the end as well, mass customization. So today, because so many manufacturing methods rely around tooling, you don't see a lot of customization. And when you do, it's very, very expensive, of course. So for example, we're looking at a couple of different gear shift knobs here for, your shifter in your car. Today, if you get into every single, Corolla or, Camry, or I have a Toyota, so I'm saying that, but, all of those are going to look the same because they have one tool or they have a few tools that are producing billions or millions of these parts a year. That's really because they're tied to these tools. In the future with, things like the production system and the shop system, we can now, actually customize our parts for end users. Users are able to decide what they want because we're printing these components. It doesn't add any cost to the part. It doesn't add any lead time to the part because we're just simply changing the model and, uploading it to the printer and printing a batch of those. So it really allows us to produce better parts for our end users, allowing them to decide exactly what they want. We can design specific parts for specific regions to allow for this mass customization that really leads to better components and better parts. We're seeing a lot of embracement of mass customization, especially in the jewelry industry. You can see here, this is a perfume ornament. It's used to attach to a perfume bottle to really spruce up the design, spruce up the look. And you can see this design is really cool. It actually features a ball that was printed inside of this outer sphere that can never be removed to really, a really cool design that really spruces up this idea. And of course, with jewelry, you can think of all the tooling that's involved in the jewelry industry for each different design they want to manufacture, each different size they want to manufacture. So the ability to just be able to print these components is very beneficial. A couple more jewelry components here. You can see these designs. The one up top is really cool as well. All those parts spin within each other, and they're all printed together to attach to, I believe that's to a blouse, and then to another leather component here. All in all, just sticking on theme here, that again, now we're able to mass produce these parts, mass customize components to allow people to print what they want, when they want them, specifically for their end user. All right, let's quickly wrap up, and then I'm happy to take a look at the questions and answer any questions anyone has. And of course, you can feel free to email me as well. So, quick wrap up. What was A.E.B.E 1.0? A.E.B.E 1.0, most of the applications were these very high part costs, these very slow processing times for these very specific low volume applications. Seeing lots of those applications in aerospace and medical device. You also, something that we didn't talk a lot about today in plastics, but A.E.B.E 1.0 for plastics was really this extensive prototyping jigs and fixture stage. You saw lots of that in plastic, but it was almost always always too expensive to produce those parts in metal because the processes was just too expensive, too slow, and too inaccessible. Now, moving to additive 2.0, we're seeing this highly accessible metal 3D printing technology. Parts that just never could have been justified to print with traditional metal 3D printers can now be printed easily and affordably. So, you can see a lot of different geometries here on the screen. All these parts are printed on the studio system, easily and affordably in an office environment. The other side of additive 2.0 is really binder jetting as a means of mass production and end-use components. So, both this process and product benefits, quickly to remind you, this tooling-free manufacturing option, supply chain re-engineering, and all these new design features and mass customization that really allow for, better products, better end-use components, and really parts that are optimized for the application, less so for their manufacturing. All right. Thank you, everyone. I'll stick around here and I'll take a look at the Q&A. I really appreciate you taking time out of your day.
Αυτό ήταν από εμάς. Σας ευχαριστούμε πολύ για την παρακολούθηση. Θέλω να σας ενημερώσω ότι το εργαστήριό μας παρέχει binder jetting τεχνολογία σε εκτύπωση μετάλλου, καθώς και το FFF που παρουσιάστηκε στην αρχή, το Studio System. Για οποιαδήποτε άλλη πληροφορία χρειάζεστε, είμαστε ανοιχτοί προς εσάς. Μπορείτε να βρείτε τις πληροφορίες μας στο προφίλ της Lino Group, στο Virtual Συσκευασία. Σας ευχαριστώ πολύ για ακόμη μια φορά. Καλή σας συνέχεια.